Okay, can everybody see the screen?
Yep.
Yes, great. Thank you. Thanks for putting this together, Mark, and having me. I want to start off by saying a little bit about me. Like I said, I work at Galois, which is a company in Portland, and essentially what we do is research and development for government and industry clients. And one of our specialties is developing programming languages, programming language tools in order to build reliable software systems. And so that's sort of my specialty, my background. And that's sort of my perspective coming into quantum computing. I started working on quantum computing in 2015. So before I was at Galois, when I was a grad student, I hadn't taken a physics class since high school, but I worked with some great collaborators and sort of stepped into this new field. And what I found was so interesting is that it was very accessible to me from somebody who is a computer scientist, who is a programmer. And so that's sort of the perspective that I'm going to bring to this talk. Hopefully it's not going to be a very physics talk. It's going to be a computer science talk. So with that in mind, I want to jump in, but before we do, I would like to say that I'm not super, I can see the chat, but I'm not super confident about my ability to always notice when a new thing happens. So I would prefer if you interrupt me speaking. If you do say something in the chat, I will do my best to notice and respond, or somebody else could notice and speak up. Any of those options should work. So great, so let's get started. So I want to sort of start from a shared perspective. And to me, that starts with how do I interact with a quantum computer? So the way that I'm going to think about it for the sake of this talk is that it's a black box that takes in some circuit or some we can think of as instructions, and gives us back some probabilistic measurement results. Okay, so what does that mean? So a circuit is a little diagram like this. We can think of it as instructions of how to apply gates or certain operations to wires or qubits, which consist of qubits or bits. So here, the single line represents a qubit. And so it says, construct a qubit in the 0 state, apply the Hadamard gate, that's the H, and then measure it, which will produce a bit. It will probabilistically produce a bit. And so the bit is denoted by the double line. So the quantum computer will receive these instructions, execute them, and give us back some results. And so in this case, it's going to give us either 0 with probability 1/2 or 1 with probability 1/2. I'm going to try to graphically do a little bit of representation with coins. Heads is 1, tails is 0, and then I'll use this combined state for probability distribution. Yes, I know that these are different coins. It was useful to have them be different colors. Okay. So as a programmer, you know, if I'm using these circuits to tell the quantum computer what to do, I want to think about what are some features of these circuits. In other words, what are the programming abstractions that I can build on top of them? So I said that circuits we could think of as gates applied to wires. and that's true, but there's other layers of abstractions that you can sort of layer on top of these. So one example that I'm going to use a lot is in this talk is a controlled circuit. So for example, this this dot with the vertical line coming down, you'll see this as a control for both qubits and also in this case bits. And essentially what it says is perform this first measurement, this first operation. If the result is a heads, then we'll apply the controlled Hadamard to the result, which means that we flip another coin, essentially. On the other hand, if the result of the first measurement is tails, then we won't apply the Hadamard gate, which means that the second result is going to stay 0. So it will still be tails. So this circuit is essentially how you'll often draw it. You'll often see it in these quantum circuit languages. But as a programmer, a much more intuitive abstraction is as a conditional, right? So we give a name to the measurement results, let that be B, and then we say if B, then flip another coin, or else output 0, output tails. So I want to mention this as sort of a level of abstraction above what really is a circuit, right? It's where this is a program that essentially constructs a circuit, but at a high level as a programmer, we're thinking of it as its own abstraction. Okay, so some other features of circuits that are important for programming purposes. Circuits should be compositional. That just means that if we have two components and they have the correct interface to be plugged together, then we should be able to plug them together so that we can build up larger programs out of smaller ones. Seems pretty straightforward. In addition, as we go beyond just describing specific concrete circuits, we'll often want to describe families of circuits. So functions that are not just, that are parameterized by either the number of qubits that it takes as input, or a parameter like a rotation gate, or the number of times some operation is iterated. So as a concrete example, we can take our flip circuit from earlier and think of the sort of plain flip as the 0th iteration, and then we can control that by iteratively controlling the next flip by the result of the previous one. So this first controlled flip circuit will give us 1 with probably 1/4, because we'll flip the first circuit, we'll flip the first coin and only flip the second one if the result is heads. And we can of course iterate that to 3 flips or to n flips, which will give us 1 with probably 1/2 to the n. Any questions about this so far? Okay. So the last feature of quantum circuits that I want to bring up is the one that's, I think, most relevant to this question of quantum verification. And that is, quantum circuits have mathematical meaning. So what does this mean? I said that the behavior of this n-ary flip operation is going to give us 1 with probably 1/2 to the n, and 0 with the remaining probability. So describing the semantics of our programs, we'll often think of them as specifications for classical programs, right? This is what this function does. With quantum computing, we can describe a specification in terms of a probability distribution like this, but there are actually even richer mathematical descriptions. In particular, we can describe not just the probabilistic specification of the measurement results, which is what we've described here, but in fact, we could describe the behavior of a quantum program as a probability distribution over quantum states. So these are encoded via representation that are often called density matrices. And so this flip circuit is going to be the semantics is going to be represented as a probability distribution that is, sorry, a probability distribution over quantum states. So now no longer just a probability distribution over bit 0 and 1, but now over the underlying quantum state. And the benefit of this is that now we no longer have to just reason about the classical output of our circuits, but in fact we can reason compositionally about the quantum behavior of our programs as well. There are other kinds of representations of semantics of quantum computations, but it's important that we have some kind of representation because that's what lets us describe what our programs do. And when we're working in a setting like quantum, where the behavior of our programs is not intuitive, I think it's even more important that we have those features. So are there any questions about that idea? I'm not going to go into the details of what these density matrices, how these density matrices work, but you can find them in lots of resources. Okay. If not, I'm going to, I want to just give a pretty brief overview of quantum circuit programming languages that exist in practice. I'm calling these circuit languages because essentially they're all conforming to the sort of circuit model of quantum computation that I described before. There are some attempts to raise the level of abstraction so that the programmer is not actually thinking about circuits themselves, but the popular languages that we have now are almost all adhering to this model. One of the most popular is Qiskit, which is IBM's Python framework. And so this is a language that is essentially a Python library, a Python framework that lets you write a Python program that will construct a circuit. So this is an embedded language essentially, and the benefits are that you can use these high-level features of Python in order to combine circuits together to build up a large program. Qiskit also has a very active community, and it allows you to interface with IBM technology. Q# is another language. It's developed by Microsoft, and it's more of a standalone language. So instead of being embedded in Python, it is its own language. And they also have their own libraries, simulators, optimizers, debuggers, etc. A lot of the ideas that Qiskit and Q# are based on are derived from a language called QWIRE, which I quite like. It's a functional language that is embedded in the Haskell language. And it really pioneered a lot of the ideas of types, parameterized circuit families, and so on. And I think it's a really neat language. And then I also want to mention Project Q, which is an interesting framework, also in Python, I believe, which has features for converting between different low-level circuit languages, and it's quite an interesting feature. So there's a number of other languages that I haven't mentioned here, but I just want to give a taste for a little bit about the infrastructure. Yes, thank you. Microsoft does not like to call Q# a circuit language. I interpret it as a circuit language, but they do try to frame things as a higher language. So thank you. I can't debug their blog. I can't refute their blog post right now, which was in the chat. But one thing that's missing from these languages are a connection to the semantics. So what do I mean by that? So circuits, I said they inherently have a mathematical meaning, right? We can describe what they do. But in order to connect that to real programs, you have to actually implement the semantics in a way that is a formal analysis of the entire language. So, you know, these languages are quite complex, and they have a lot of features, and those features are really good for expressivity, and they are what make up a language. But those features often, it might not be clear what the semantics is, essentially. So in order to reason correctly about what your program does, you really have to account for those language features. Now, when we're talking about a language that's embedded in Python, like Qiskit, in order to reason about it, you might have to argue that you need to reason about all of Python. Python is difficult to reason about the semantics of Python. It's quite a complex thing. Furthermore, you know, on the other side of things, there are a good number of academic programming languages, quantum programming languages, that do have formal semantics, that do describe, here are the language features, and here are what they mean in terms of either density matrices or some other mathematical representation. But these tend not to be implemented in code. They tend not to be used very richly, and or else they are, you know, still sort of prototypes, which is an example of proto-QWIRE, which is a sort of, I don't know why it's called proto-QWIRE, because it's came after the original QWIRE, but it is intended to be a formalization of QWIRE. So, so the work that I want to talk about in the rest of this talk is work that I developed at UPenn with my collaborators, which is called QWIRE. And I pitch QWIRE as a high-level circuit language with a formal semantics that is embedded in, and the reason why its semantics are accessible is because it is embedded in a language called Coq, which is a proof assistant. So what that means is that we can not only write programs, compute circuits in this language, but also state theorems and reason about the correctness of those circuits inside of Coq. As concrete, to get an idea of the syntax, which we're not going to really go into it in the rest of the talk, but to get an idea of the syntax, here's a little diagram, and here's a representation of that diagram or of that circuit in QWIRE. And essentially it says, apply this gate to the wires Q and R. We're going to name the outputs and call them Q prime and R prime. And then we'll apply a measurement gate to Q prime. And then we will output those two wires. So a bit B and the qubit R prime. Sorry, yeah, I skipped that. So why are we doing this? Why is it important to reason about the semantics of your program. You know, maybe it's an academic exercise, like what's really the point? Well, the point is bugs, right? If you write down a quantum program, you want to know that it does what you think it does. So what could go wrong there? Well, you know, one option is that you may have how do you know that the algorithm that you're basing your code off of is actually producing the right result, right? Of course, we can, typically what I would do as a programmer is write some things down on paper and make some either informal or formal argument on paper that, yes, this is actually producing the result that I think that it is. But there's also a subtle gap there, which is the difference between the implementation and the algorithm. So an implementation and the specification. And you know, this is essentially the source of what we usually think of as software bugs. And in classical programs, we'll address this via a whole host of methods. Unit testing, you might have debugging tools that like breakpoints and things like that. And we also have formal methods for classical programs. So essentially saying that the implementation doesn't match the specification is essentially saying that, well, we've written down a program, which we've called flip, and it turns out that it is not actually achieving the specification, that it doesn't produce this density matrix. It doesn't produce this probability distribution that we think that it should. Paul, is there something that you wanted to add? I don't quite understand the comment. Okay, that's fine. Okay, thanks. All right, so so we have some approaches for debugging programs, for debugging classical programs. So why don't we just use those for our quantum programs? Okay, so option one is to test it. That sounds good. We should definitely test programs. But there's a couple of subtleties here that make testing difficult. For one, measurement results, which are the things that we can test, are they're probabilistic, right? So in order to run a single unit test and say that I expect this input to give me this output with some probability, you can't just run that unit test once. You have to run it some large number of times so that we can get out a probability distribution, right? Okay. Second of all, I'll say that testing is already imperfect because we can't test all of our inputs, right? Of course, there is an art to picking good test cases that you expect to cover the corner cases of your program, but there's always a possibility of bugs that your tests don't catch. Two, there's a question of, are we testing this program on an actual quantum computer, or are we testing it on a simulator? If we do it on an actual quantum computer, of course, that can be very expensive to gain access to that. And we also have limitations in terms of the quality of those results. So things like noise and error can interfere with the operations that we're doing, which, you know, of course, ideally we would be able to correct for those features, but currently we can't. So any test that you would run on an actual quantum computer would be subject to additional noise, which would obscure the test results. On the other hand, if we were to run those tests in simulation, then we can't test for we can't test for inputs of any large size, right? Because that the state space would explode. We can't simulate arbitrary quantum programs. I'll also say a problem with testing is even if we find a test case, we can't debug it in the usual way. So we can't look into a quantum computer and look at breakpoints or see what the computer is doing at a particular point in time. So just the limits of the quantum hardware mean that we can't do that debugging in the same way. So I mentioned, so I think simulation is an interesting tool. Simulation doesn't necessarily have to be accompanied by, well, the benefit of simulation over unit tests is that we no longer have to worry about necessarily the probabilistic results, because simulation can explore all the different probabilistic results. However, then by definition, this only works for small inputs. And so we're going to miss out on a lot of bugs just because we lose access to that. So I think I would say, finally, the last option is to reason about the behavior of the implementation formally. And this only works if we have a formal semantics of our language and we have a way to reason about it. So this was sort of the motivation behind doing this formal verification, is if these other tools for debugging and ensuring the correctness of our quantum programs don't work for near-term quantum programs, then we should enable formal verification in order, as part of sort of our development process, as part of our way of knowing that we've written the right program. And in order to do that, we need a semantics for our language. And as I said before, this is because pen and paper proofs are not connected to the implementation. And we need a formal way of connecting these proofs to our implementation. Okay, so what is formal verification? I do apologize because we've gotten pretty far into this talk without actually saying what this is. But essentially, formal verification is a proof system. So it's a way of reasoning about what your programs do based on a small trusted core. So we start with some baseline truth and ways to prove facts on top of it, and then we build up from there. So in this case, we're going to formalize the semantics of circuits inside of a proof system. And what that's going to look like is if we have a circuit C and a density matrix, rho, which is one of these matrices, then we can apply the semantics of C to rho, and that's going to give us a new density matrix. So in other words, the rho is the input state. So if our circuit takes in some quantum state, it will also produce a quantum state. And so what's nice about this is that we don't have to reason directly about the probabilistic behavior of C, because the semantics of C, this bracket C, is just a function from a probability distribution to a probability distribution. And then finally, we can use this semantics in order to prove the correctness or properties of the circuits that we're interested in. The system that we developed to do this is called QWIRE. It is embedded, as I said, in the Coq proof assistant. You can find it on GitHub here. And let's look at what that would look like. I think maybe I'll pause for a second if anyone has any questions, and then I'll move on. Okay. So formal verification comes with a number of trade-offs. on the plus side, the proofs directly connect your code to your specification. So what that means is that if your code changes, then your proof also has to change with it. This may or may not be automatic. There are some proof systems where the proof can be more automatic. And so if your code changes, then it will automatically run the proof again and be able to solve it for you. QWIRE, the system that we developed, is not actually automatic, it's interactive. And so that means that if something, I'll say it's semi-automatic. There are a number of semi-automated procedures that will help you prove facts that may be robust to changes in your code. But in some cases, you may have to update proofs in order to reflect the changes. However, the code will tell you if the proof has broken, and that's an important part. That means that the proofs cannot get too far out of sync with your code as long as you're paying attention. In addition, the proof will break if you introduce a bug into your code, and so that's good to know as well. The second pro of formal verification is that these proofs are formal and precise. And what that means is that you are not allowed to skip any important details. So if you're reasoning about a program on paper, it's pretty easy to mess up on paper. Yeah. You know, as I said before, you might forget about a case or a corner case or make an assumption that doesn't actually hold. Formal proofs don't let you do that. But on the other hand, you can also use some high-level reasoning techniques to overcome those small details. So things like induction. If you have defined your circuit by recursion like we did for flip, then you can prove a property of it using induction, which we'll see soon, which is quite a high-level technique. But as a con, formal verification is, as a rule, quite a lot of work. So, you know, I said that the proofs don't let you skip any important details. And although we can use high-level reasoning techniques, it often can get quite into the weeds in order to proceed. So you might find yourself being hung up on proving some fact that if you look at it intuitively, you say, of course this is true. But you have to convince the proof system that it's true, which is a harder problem. So I want to give an example of what this looks like in practice, of what proving a property looks like in practice. So here's a theorem that we have about the unary, or I guess this is the single flip circuit, the coin flip circuit, right? So this is the circuit on the top right, and it's just flipping a quantum coin. And so what this theorem says is that the output of that coin flip should be the density matrix, the probability distribution of either the state 0 or 1 with equal probability, 1/2. And those are the two corners of the matrix. So the way that we interact with these theorems in Coq is that we will apply a number of tactics which slowly break down the goal into manageable pieces. And so the proof script, as we call it in Coq, says we start off with the keyword proof, and then we write down some tactics, and then we end at the end with the keyword QED. And when we apply QED, that will only process if we have actually proved all of the entire theorem. And if QED doesn't process, then you haven't proved the theorem, and if it does, then you sort of get this feeling of, yes, we've proved the theorem. That's great. Excuse me. So, so in addition to these tactics, we use these tactics to manipulate a goal. So right now our goal is just the statement of our theorem, but as we apply tactics, the goal will change. So for example, in this case, we will start off by using a tactic that we wrote, which is called matrix denote. And all this does is unfold the definitions of coin flip and the denotation function, right? So so essentially it unfolds coin flip to be the circuit that I've described above, and it unfolds the denotation function into matrix operations. And so we have replaced the left-hand side of the equality with some sequence of identity matrices and tensor products and matrix multiplication and Hadamard matrices, etc. So then the next step, we would apply a tactic which simplifies the left-hand side using some known identities. So all of that noise from the previous slide can, we have a lot of identity matrix multiplied by something. Those can all be cut out, right? So all that simplification reduces to something that looks like this. It's a lot more readable. And then essentially we can solve that equality by brute force. We wrote a tactic called solve matrix, and it essentially just computes out the matrix and then checks for equality. Now, this is all very good for a small circuit, right? This is a circuit with just essentially one qubit that goes through the whole thing. But that's not going to work in practice because the matrices, the semantics of our programs would get too big. So we came up with some sort of rules which worked for QWIRE in order to proceed a little bit more strategically. For example, rule number 1 is only use brute force. So in other words, the techniques from the previous slide for small cases, for small matrices. That makes sense? So in this case, when we have our n-ary flip circuit, the 0th case is just going to be trivial. So in the 0th case, we just output, in this case, true. Okay. And if we plug in 0 in the specification below, we'll see that that should give us 1 in the bottom right-hand corner with probability 1. 1 over 2 to the 0 is 1. And so we can easily check that that is in fact meeting the specification for n equals 0. On the other hand, the definition of the n-ary flip operation when n is equal to n prime plus 1. So here, this match statement is doing a case analysis on n, and we're now looking at the case where n is equal to, S here stands for the successor of n prime, that is n prime plus 1. And the definition of flip is going to be, well, first we flip the coin n prime times, and then we use that to control another coin flip, right? This is a generalization of the binary case. So, so now we want to prove that this definition meets our specification, right? And how are we going to prove that? Well, by induction, by using the induction hypothesis. So this is the statement of our correctness theorem for flip, modulo making it look prettier in line with the talk. And the first tactic that we apply is Cox induction tactic. And what that will do for natural numbers, which is what n is it will let us consider the n equals 0 case, which I said is easily provable by brute force, and then consider the n equals n prime plus 1 case. And this proof here generates an induction hypothesis. So it correctly generalizes our theorem and says flip n prime has the correct specification. And then we use that to reason symbolically about the fact that now flip n also has the correct specification. So just as you would do it on paper, essentially we're now doing it in a formal theorem setting. And this is really powerful. There are other verification systems that don't necessarily, that can prove formal facts about concrete circuits, so a circuit of some particular size, but can't necessarily reason about parameterized circuits. And so what that means is that we don't have to reason about the flip circuit of size 100. We can reason about it of size any n. The third rule that I want to bring up is not even reasoning about, not even going into the matrix representation at all, essentially. And by that I mean we can use equational reasoning to rewrite circuits into simpler versions. Sorry, we have a question. Would the proofs use eigenvalues typically? I'm not sure what exactly you mean. I think that might depend on what you are trying to prove. Like the proofs of correctness that this particular program implements a specification, like the ones that I was showing you. I don't think that there's any particular special reasoning about eigenvalues, but if you have a proof that you would write on paper that uses a particular proof technique, I like to think that you can replicate any of those paper proofs in Coq. I don't know if that answers the question. Excuse me. Okay, great. Right, so the sort of third approach to reasoning principles is to define some equational reasoning properties. So for example, if we have any circuit that has a unitary operation followed by the unitary's conjugate transpose, the conjugate transpose of the unitary is always its inverse. And so I can always reason for any such unitary, if we apply u dagger after u, that's going to be the same thing as the identity. So we can, the theorem that I've written here exactly says that. This triple equal sign is shorthand for any input state row, the semantics of C1 is equal to the semantics of C2 on row. But the triple equal sign makes it so that you can use that identity inside a larger circuit. So that means that this not only holds for this particular circuit, but it holds for any circuit where u followed by u prime exists. So we can use this equational reasoning principle to think about things like circuit optimizations. So circuit optimizations work right by identifying some pattern inside of a circuit. Well, one way circuit optimizations work, by identifying some pattern and then replacing that by an optimized pattern. That's essentially what u followed by u dagger is. And so by doing this equational reasoning, we can argue that all of these optimizations are actually behaving correctly. They're actually not changing the semantics of our circuit. So, so I will say, actually, I'm going to skip ahead a few slides. This idea of verified optimizations generalizes to a verified entire compiler stack. So, and this is work that I was not involved in, but that was done by my collaborator, Robert Rand, and a group that he worked with at the University of Maryland. He's been working with them for a few years. And so the idea there is to use formal verification in a system that is builds on top of QWIRE, essentially, to verify optimizations and compiler passes. So on the left-hand side here, we can see sort of a map for starting with a high-level language like QWIRE, Q#, etc. Compiling this into some sort of intermediate representation like CHASM or QUIL, those are existing intermediate representations. And then turning those into QWIRE, which is an intermediate representation for quantum circuits that this team has developed, for which they have a formal semantics, and they can verify the correctness of compiler passes of optimizations. And so these optimizations are all verified to be correct, not preserve, to preserve the semantics of the circuits. And those can then be transferred back into other intermediate representations that can be compiled to hardware. So there's still a possibility that other bugs could be introduced by other optimizations at a higher level, but this is one path forward for verifying the correctness of compilers. Okay, so I just want to sort of summarize some of the work that has been done in QWIRE. At a high level, we can verify the correctness of particular circuits or protocols, like teleportation, Deutsch's algorithm, etc. And that can be extended, as I described, to families of circuits, like inductively defined circuits, in a way that is actually scalable because we never have to compute a large state. And then there's been this work on verified compilers and compiler optimizations, so that the entire software stack that you use to run your programs isn't introducing more bugs that didn't already exist. I think what some of the features that make QWIRE a good tool for this is that it is quite a small language. Its features, its expressivity mostly comes from being embedded inside the Coq interactive theorem prover. But on the other hand, it's not really suitable for production systems. Coq is an academic language, and so the interactivity of Coq, the way that you have to prove the theorems incrementally, is not well suited for people developing each new program. They might not want to have to learn how to use QWIRE in order to prove properties about it. There are some other more automatic proof techniques, which I think are really interesting. And there's a lot of future work to be done there. QWIRE, however, QWIRE does have a lot of good features, and that includes a strong type system that both prevents ill-formed circuits from being constructed and also describes things like how many qubits a circuit operates over. So that way, you never have to worry about, say, applying a circuit that expects bits, that expects classical qubits, for example, to the wrong state. And of course, it has a denotational semantics, which is formalized in Coq, which is, I argue, extremely important. So there's a lot of work in the space of verified quantum computing. It's really interesting work. As I said, there are more automatic solvers which work for concrete circuits. There are other techniques that are based on very interesting and unique representations of quantum programs, such as the ZX calculus. There's also different kinds of proof techniques, such as those based on program logics, like quantum Hoare logic or quantum relational Hoare logic. We can apply formal methods in different kinds of applications and specialize them to those applications, which can lead to easier interfaces, so easier use, ease of use, and use formal methods to reason about, use formal verification to reason about different kinds of features, not just functional correctness, right? Things like how much error is introduced by this program, or how robust is it to error over time. So that's about all I have. I just want to sort of end with this idea which is that there are trade-offs to formal verification, but in my opinion, it is often worthwhile. In particular, I think quantum computing is is an area where verification provides a lot of benefit because of its lack of support for things like debugging in other areas. So that's my takeaway. If there are any questions, I would love to chat a little bit longer, but thank you very much for listening. Okay, I see a question about Galois and how much we focus on quantum computing. Right now, not too much. So we are a contracting business. So our work relies on working with customers who have these problems in computer science. So one thing that I'm actively doing is trying to connect with customers who might be interested in learning more about this and continuing on some of this work that I had started in graduate school. Some of my colleagues are also interested in working in this, so it's not just me. But so we are learning more and trying to think about the big problems in quantum computing, and hopefully we'll be doing some more work soon.
Are there any other questions? Okay, if not, thank you so much, Jennifer. And I will see everyone in 2 weeks when Stephen Bleidler from Portland State will be joining.
Thanks all.